In this video, we're going to discuss how we can measure conditional probabilities using a joint density function. A conditional probability density function is a measure of the probability of one event occurring, holding other variables constant. In the bivariate case, the probability of y conditioned on x is defined to be the probability that the variable y takes on the specific value of yj, given that x equals some specified value. Similarly, the conditional probability of x given y is the probability of observing each particular value of x, such as x equals xi, given that y is equal to some specified value, yj. With a conditional probability, we're not looking at the probability of an event in the entire population. We're looking at the event in a subset of a population where some specified condition holds. As you learned in your introductory statistics course, the probability of y given x is equal to the joint probability divided by the marginal probability of the variable that you're conditioning this on. In the example that we discussed in the last video, you might be interested, for example, in determining what the distribution of income is like for a person with a given level of educational attainment. That would be an example of this type of conditional probability. In the numerator, you would find the probability of observing those two events together in the population, and in the denominator, you divide by the probability of the event that you're conditioning this on. Similarly, the probability of x given y is, again, the joint probability of observing those values of x and y divided by the marginal probability of observing that specific value of y. Let's construct an example of a conditional PDF. Suppose we want to find the probability that someone has a low income conditioned on the event that they have a high school degree. The formula for that is that we take the joint probability of those two events and we divide that by the probability of the event we're conditioning on, which in this case is having a high school degree. So the numerator would be the joint probability of observing a low income for someone with a high school degree, which in the table would just be the element in the second row and the first column, which is 10%. So the numerator of this is 10%. The denominator is the marginal probability of observing someone with a high school degree. And we know that to find the marginal probability of that, we add up all the elements in the second row. So that would be equal to 10% plus 32% plus 5%, or 47%. So we end up with 10 over 47, which equals 0.21 rounding, or 21% of the population. So conditioned on having a high school degree, the probability that someone will have a low income is 21%. Similarly, if we wanted to find the probability of a medium income for someone with a high school degree, that would be 0.32 out of 0.47, or the probability of a high income, given that someone has a high school degree, would be 0.05 out of 0.47. And if you want to verify this, if you add up all those probabilities, that would add up to 1. So a conditional probability density function satisfies the same condition that we observe for any other probability density function. Each individual probability is between 0 and 1, and the sum of the probabilities over all possible outcomes add up to 1. We can also measure conditional expectations, and those adjust the expected value of a variable holding constant the level of another. So if we find the conditional probability of each event, to find the conditional expectation, we just take each outcome and we weight it by the conditional probability of observing that. If we have a bivariate regression relationship, such as the ones we talked about at the very beginning of the class, what that regression line is essentially giving us is the expected value of y given the level of x. This relationship here is essentially what underlies the regression equation. Specifically, this first equation is telling us, on average, what the level of y will be for each and every possible level of x. And the regression equation is essentially going to be assuming that the average value of y is in fact a linear function of x.